There we go. Just recording this. So, any homework questions before we get started? Are we good? Okay, so let's look at some questions from the final section, section 5-6. And it's called, I think it's called, its full title is Simple Harmonic Functions. So quite a lot of the questions take the form of, here is a function, a harmonic function. Find the amplitude, which we know how to do. Find the period, and find the phase shift, and then they add an extra thing called the frequency, right? So let's take an example. Suppose I had 4 the sine of 2x take away pi over 3. That is an example of a simple harmonic function. Harmonic, it comes from the functions typically a sine or a cosine, and it's not just a simple sine like the sine of 2x, right? It's got bits to it. Now, there are 4 features that you get from this, 3 of which you've seen before. The first number, the first feature, is the amplitude. Now, the amplitude is always a positive number, and it's the number that goes here, right? So if it's 3 sine x or 4 cosine x, then the amplitude is 3 and 4, always positive. The second thing that you can get is the period. Now, the period of a function represents how, along the x direction, how long it takes for the sine curve, in this case, to repeat itself. And there's a formula for it. If it's radians, which it typically is, it'd be 2 pi divided by this coefficient. So the period would be pi. Right, we're comfortable with amplitude and period. You've done it for other situations, nothing too new. And then we've got phase shift. Now, phase shift is a little bit less clear because there's 2 versions of how you write one of these functions. One of the versions looks like this: 4x plus pi, 2x minus pi upon 6. There is no factoring going on. It's just a pure 2x, 3x, 5x, plus or minus a pure pi, pi upon 4. When it's got that form, you can get the phase shift by taking this fella and dividing it by that guy. So in this case, the phase shift will be pi upon 6. So you take this number here, which is pi upon 3, this fraction, and you divide it by the coefficient of x, and that will get you the phase shift. If, however, you get it written that way, where the thing inside the sine has been factored, you see how they've pulled out the 2 and called it x minus pi upon 10 in this case. In this case here, the phase shift doesn't involve you doing anything. It's just the pi upon 10. So it depends on which way they write the harmonic function. Do they write it basically with nothing going on, just a pure data? In which case, this guy divided by 2 gets you the phase shift. Do they give you it in this kind of factored version, right? 2 lots of this thing, or 4 lots of that thing. In which case, this fella here, right, is going to be the phase shift. And you don't do anything, it's just untouched. We cool? Any questions about that? Now, I did say that there was a 4th thing. So let's introduce that idea. It's called the frequency. Now, it gets its name because a lot of simple harmonic functions, a lot of sine and cosine functions like this, are used in science where you're talking about waves. It could be sound waves, it could be light waves, it could be the waves in an ocean. I mean, any kind of wave. And the word frequency is used. You know, you could have frequency that says a particular sound has a frequency of 5,000 hertz, which is just 5,000 cycles per second, right? That would be a sound wave. If you talk about the waves on the ocean, you could say that from one peak to the next, they were passing by you at 10 cycles per second, 10 hertz. So that would be a very fast kind of current, but you could imagine it. The formula for getting the frequency is actually very simple. It's 1 over the period. So you've already calculated the period, so all you need to do is 1 over it. The way I think of 1 over something is I think of it as the reciprocal of the thing. So to give you an example, see this top one here? If I do the period, it was pi. In this question, then, the frequency would be 1 over pi, right? Suppose a different question. The period was pi over 4. Then in that case, the frequency would be 4 over pi. You know, if you find the reciprocal of a fraction, you essentially turn it upside down, right? The top becomes the bottom and the bottom becomes the top. So if you know the period, you pretty much get the frequency for free. We'll do one last one. Suppose that the period was 2/3 pi. Okay. Now, what would the frequency be for this last one? Take a volunteer.
3/2 pi.
Are you 100% about the pi? Because the way you said it isn't quite the way it needs to be said.
Well, when you put it that way, no, I'm not 100% sure about the pi.
Right. Should the pi be in the top or the bottom?
The bottom.
The bottom, 3 over 2 pi.
Yeah. Now, you might have meant that, and the way you said it is correct, but if you hear it another way, which is how I heard it, I heard that. Now, did you already mean that? In which case, we're good.
Yeah, yeah.
Right. I guess the only way that you can cover that up is to say something a little bit long-winded, like 3 over 2 pi or something. Because 3 over 2 pi is correct, but it is possible to interpret it in 2 ways. So you were okay if you thought that. So far, so good? Yeah. Now, if you put, let's do a different harmonic. Sometimes you get the added question of sketching it. Well, not so much sketching it, but comparing it against other things, right? So, actually, I have got this one. Why don't I use this one? If I was looking at what does this thing look like as a sketch? Well, it's a sine function. And so it would start life off as going up and going down, and it would do that. Its period is pi, so that would make this thing pi. It'd also make this 0, this would be a 1/2 pi, and so on. since its amplitude is 4, I would know that would go 4 and that would go -4. So what I've got in front of me here isn't quite this guy. The fellow that you see right now is very similar to it. But he's not that guy. He's that guy. So the only thing I need to do to this picture is to factor in the phase shift. Now the phase shift in this case was plus pi upon 6. That makes everything here move pi upon 6. Oops. Right. So the red guy is him. So amplitude adjusts how high up and down the thing goes. The period tells you start to finish for one cycle. And the phase shift just takes everybody and either moves it right or left a fixed amount. In this case, the phase shift was pi upon 6. So that guy there would be at position pi upon 6, for instance. We cool on that? Normally when you get these questions, there's 4 of them, and one of them is this guy. And the other ones do all sorts of things that make them a little bit different. For instance, see the 4 and -4? It might be 1 and -1 in one of the wrong pictures. Or they might make the period 2 pi instead of pi. So when you look at the 4 pictures, apart from the one that's right, the 3 that are wrong probably have some of the features, but not all of the features that your answer should have, right? It may have everything right, but they got the amplitude wrong. It went up to 1 and down to -1. Or they may have got everything else right, but the period was 2 pi instead of pi. Or the phase shift was not pi upon 6 moving to the right, but maybe they'll move it to the left pi upon 6. So if you scan through them, you can quite quickly tell what it is. I like to kind of draw a little bad picture like this, and then I look at the 4 choices and I say, okay, the one that looks like this is number 3 or it's number 1, and that's how you should kind of choose it. Are we cool with that? Right. Do you need another example of the harmonic, or do you want me to jump back and look at some of the earlier sections, the other 2? Any choices in the matter? You don't mind? Okay. Let's look at inverse sine and cosine functions. Well, actually, inverse trig functions, to be precise. There's an inverse sine. Here is an inverse cosine. And the last one I think we need to worry about is inverse tan. So I'm going to look at what do those functions look like, right? What's their shape? Most of the questions you get, in fact, involve you finding out what the answer to things like what's the value of the inverse sine of √2 over 2, or what's the value of the inverse tan of 1, something like that. So it'll take me a few moments to get the calculator set up. So that's what I'm doing. Just getting some things cleared up. Okay, here goes. And there we are. Just doing a check. Are you all looking at the calculator? Right.
Yes.
Right. So the inverse sine function is obviously by its name, it's the inverse of the sine function. In other words, if x gets you y, y gets you back to x, right? It's a bit like x squared and its inverse function is the square root. And so if we go to the calculator and I type in inverse sine of x, and I'll make sure that I'm in radians, which I am, I should simply just go to my window. Now, the first thing you need to adjust here is that the inverse sine function returns, like the inverse sine of root 2 over 2 or so on. It returns the angle that would give you that sine. And there's kind of weird rules about what it is and what it's not. So the first thing is that the inverse sine has a domain from negative pi upon 2 to pi upon 2. Now, what that range of angles covers is that it covers the first quadrant and it covers the fourth quadrant. In the first quadrant, you'll get all the inverse sine numbers, and in the fourth quadrant, you get all the inverse sines that are negative numbers. So if I was finding the inverse sine of negative root 2 over 2, the answer I would get would be an angle in the fourth quadrant. If I was finding the inverse sine of a half, I'd be finding an angle that has a sine of a half. I'd get it in the first quadrant. Now, if I do a little zoom to fit on this fella, that's what the inverse sine function looks like. Now, if you kind of turn your head to the side, can you see it's really just a sinusoidal curve rotated? It has to have these two restrictions. You can only use, you're only going to get answers right or use answers from here to here. And it only gives you one result. So if I was getting the inverse sine of a half, which would be here, it would tell me what the angle would be, right, pi upon 6. If I wanted to do root 3 upon 2, it would tell me the angle, and so on. So that's the guy, that's what an inverse sine looks like. If I replace that by an inverse cosine, the window changes. We use 0 to pi. So when it's an inverse cosine, positive answers you get in the first quadrant and negative answers you get in the second quadrant. Excuse me. See what's happened here. Inverse cosine is good. Window. Let's try that again. I probably did something wrong. Okay, what's not happening here? Let me pause and figure out. I'm doing an inverse cosine, which is cool. I'm doing it from 0. What on earth is going on with my calculator? If I had a brain, I'd be dangerous. Okay. I know what the inverse cosine looks like, but for some weird reason, for who knows why, I can't figure out what my calculator is not behaving for. So
Are you able to use Desmos by any chance?
I should be able to use that. You're right. let's just go in here. I'll use this cell. It should do the same job. I hope. I haven't tried it with that, of course. Let's do it on normal graphing mode. Let's do cosine. I wonder if you may have to do inverse. No, it's not going to take it as an inverse. It may take it just directly, which would be really nice if it did. There we go. That's the guy that I couldn't get on my calculator. It looks like this. If you find that a little bit hard to see because the scales are. Oops. All I'm doing is, ooh, not that much. There you go. So it basically, if you turn your head on the side, you see a cosine function. Okay. Then we are.
Their old calculator screen. Don't see anything.
Make sure you're in radians.
Yeah, we're still looking at your calculator.
Ah. Oops. You have to go out before you can go in. You gotta remember that. Okay, so go out. Go back in. I'm just going into Desmos as we speak. Okay. It takes a lot of moving around stuff, which is slowly. Gotcha, right? Okay, I'll go out again and back in and you should see it. So share the screen. Where is Desmos? Here we are. So if you go up here and you type in inverse cosine, of x, that is a very small version of what that looks like. And what I was doing, although you couldn't see it, was I was taking this guy and adjusting the values to make them a little bit more, oops. There. Can you see it's basically just a pretty boring curve that if you turn your head on the side, looks like a cosine, or at least part of it does. And for any given value, it will return the sine or the cosine. And it takes values from 1 to -1 as you'd expect. And it goes from pi, which is about 3.14, all the way down to 0. So 0 to pi. Now let's get back to here and look at the types of questions you get don't really, for the most part, involve sketching them. They involve you finding the exact value of that. You can certainly plug that into your calculator, but all you get is some ridiculous, 0.1234 kind of thing. So what you got to think about is that what this function returns is an angle, and I like theta for angles. So if the inverse sine of √2 upon 2 is an angle, what it's saying is there's an angle out there whose sine is equal to √2 over 2. Now you think of it that way, you have a unit circle in front of you. Don't you just go hunting for the unit circle and you find the guy that has a sine of root 2 upon 2. Is it an x coordinate or a y coordinate that's the sine?
Y coordinate.
Right. So I'm looking for a y coordinate, which is that guy. And it's this angle in here, and the angle that does that is pi upon 4. So that makes this fella pi upon 4. That seems all pretty well and good, and it is correct. There is a problem with this, and that's why the sine, the inverse sine, cosine, and tangent have restrictions, so that they only give you one answer. Isn't there another place in the unit circle who also has a sine that's equal to root 2 upon 2? There's one over here. Now, your calculator doesn't generate two answers. It only generates the first one, and that's the answer we want. So what you have to remember when you're doing inverse sine, cosine, or tangents is to realize that you're only allowed to write down one answer, and that answer has to belong to the correct quadrant, right? And the inverse sine, cosine, and tangent, these are the correct quadrants. For the inverse sine of x, for instance, if x is positive, then you'll get your angle in the first quadrant. That's where it's going to live. If x is negative, then the angle you're going to get is the angle that's in the fourth quadrant. I know there's another one, but the one you always get is the fourth quadrant. And theta will be negative. In other words, in these questions, you end up getting the right answer is theta is negative pi upon 3, or theta is negative pi upon 2, or whatever. It's going to be negative. So if someone says to you, find the inverse sine of negative root 2 over 2. The guy that you're going to get is the guy that's down there. He is not 7/4, at least not for the sake of this answer. The answer that you will get is negative 1/4. So that's a little idiosyncrasy of this process. When you get an inverse sine, if it's positive, the answer is in the first quadrant. Don't look anywhere else. I know there's another one. Pretend it ain't there. If you're looking for the inverse sine of a negative number like this, look in the fourth quadrant. Don't look anywhere else. And if the answer you've got is, 7/6 pi or 7/4 pi or whatever it is, well, you try and remember to use the negative equivalent of that same angle. So 7/4 is actually the same thing as negative 1/4, right? You get you to the same place. If you're doing the inverse tan, same thing. Right? Positive, get it from the first quadrant. Inverse tan of a negative, get it from the fourth quadrant and make sure your answer is negative. So for instance, if someone went and said to you, the inverse tan of -1, I know that has to be in the fourth quadrant because it's negative. If you go hunting for it, it's actually the same guy that's down here. Right, it's that 7/4 guy, but you call it negative 1/4. So that's why sometimes people will do these questions and they'll say, but I got the right answer. I got 7/4, right? That's the right place for that particular situation to have. But they don't realize that the rules of the game are that you need to return a negative answer when it's a fourth quadrant, right? And a positive one, okay, in the first. So what about the cosine, which is that one I couldn't get the darn thing to draw right? Well, there it goes. For the inverse cosine, if it's positive, right? So if the angle is positive, it's in the first quadrant. And if it's negative, you only go looking in the second quadrant. So for the inverse sine and tangent, it's first and 4. And for the inverse cosine, it's first and second. So far, so good. Any questions about all that? It's mostly a memory thing. You just need to remember.
With inverse cosine,
Mhm.
if it's in the second quadrant, does that mean that theta is negative?
Yes. No, not that theta is negative. X is negative. But I'll show you what I mean. If I ask you for the inverse sine of negative root 3 over 2, right? So X is negative. What I'm saying here is that if X is negative, then theta is in the second quadrant. That's what I should say. So you go looking for your unit circle. Because it's negative, you don't look there, right? You look in the second quadrant. There will be an X coordinate, won't there? That will be that fella. So you're looking for an X coordinate that's equal to negative root 3 upon 2. What angle gets you in the second quadrant, gets you him? So hopefully you got a unit circle handy, or are you just good at remembering things? Anybody remember? What angle gives you that guy there? Right, it's in the second quadrant with an X coordinate of negative root 3 upon 2. So you imagine that's negative root 3 upon 2. Last chance for a write it. Don't. Moral of that story is you need to get looking at your unit circle, because these things should be coming more second nature to you, because there's only so many standard angles, and you should get familiar with them. Right, have you noticed that then that answer is positive? So the inverse cosine is a little bit different from the inverse sine. The inverse sine of a guy like that would return a negative answer. The inverse tangent of a guy like that would also return a negative angle. But the inverse cosine returns a positive one. It just returns a positive one that's in the second quadrant, and that works. We good? Okay. So let's make life a little bit trickier. First, start off with a nice simple situation. They very often mix and match them. This is the simplest version. If you do the inverse sine of this and then you do the sine of that answer, the answer ends up being the guy you started with. So I don't need to really do any work, because a function and its inverse cancel each other out. So if you started with root 2 over 2, you will finish with root 2 over 2. Okay? Now, then you do, and I have seen questions just like this one in the homework. Then you say, oh yeah, sines and inverse sines cancel out, the answer is 5. And in this case, it's not. The answer does not exist. And it's for this reason. The inverse sine of 5 doesn't exist. There is no angle in the universe, real angle in the universe, whose sine is 5. Since that is impossible, the question is impossible, and that's why you would do does not exist. Now, what happens when you do something like this? where it's a mixture of sines and cosines, like this fella here? Well, you kind of take it in two stages. The first stage is you find the inverse cosine of root 3 upon 2. So over here, I've got my unit circle. If I look for an angle, there'll be an angle somewhere that has an x-coordinate of root 3 upon 2. Agreed? And what angle does that?
Isn't that quarter pi?
Nope, that's root 2 over 2, but a little bit further up.
Pi over 3.
That's the one. Now you see, just having a unit circle in front of you, print one out or, I don't know, write one down on a piece of paper. You can keep referring to it. Right, now, the sine of pi upon 3 is the normal sine of pi upon 3, right? So what do? You go to pi upon 3, oh, already got it. Isn't the sine the y-coordinate? And the y-coordinate is a half. So if you were being asked to calculate the sine of the inverse cosine of that guy, the answer is a half. You see, you just do an inverse and then the sine of that answer. What about the cosine of the inverse sine of a half? Oh, let's make it negative. Make it trickier. So it's going to be the cosine of somebody, right? If you imagine your unit circle, there's a guy down here with a y-coordinate of negative a half, right? And you notice that I was looking in the fourth quadrant. I could have looked other places, but only the fourth because of the rule. Now, this particular angle, right? What angle gets you to here?
(11 pi over 6).
Oops, I don't know why that's there. Let's try it again. That guy. But we don't call it 11 pi over 6, although it is. Don't we call it negative 1 pi over 6? In a way, you could make a mistake here and it's not going to hurt you. Because once you've got that answer, don't you just find the cosine of it? And won't the cosine be this fella? And this fella happens to be root 3 upon 2. And so there is your final answer. Now, I don't know how well this is going to work, but I want to show you a kind of trick. First I'll get if you have a calculator and then you can put it on degree modes, which is certainly TI-84's job, and I'm doing it this way rather than trying to go in and out and spending 5 minutes doing that. If I then type in inverse sine of negative square root of 2, I'm going to have to move this away and then I'll bring it back because I can't really see that well. So I'm going to go inverse sine of the square root of 2 divided by 2. Okay, there we go. So you type in your inverse sine, thingy bob, and I've got it in degrees. Do I have it in degrees? Try that again. I didn't. Okay, now I have it in degrees. You see the answer is 45 degrees. And 45 degrees is pi upon 4. So if I did an inverse cosine of negative root 3 upon 2, so you'll see this in a minute. So that's an inverse cosine. You can't see the first bit, but it is, of negative root 3 upon 2. And you see the answer here is 150 degrees. You see that's exactly where it should be, and it's in the second quadrant. So it's much better if you use the unit circle, because we're dealing with radians all the time, but that's a backup plan. And time is up. So thank you for dropping in. I'll just take a quick note, everybody. Ashley A. Gascoigne. Carlos. Glenn. Olivia. Skylar. And that is us. Okay. Have a nice day, everybody. I have to zoom off to another meeting. Usual. Send me emails. You get issues. We'll see what we can do. Remember, test is on Sunday. It will be visible Sunday morning. And the test is on everything we've done week 3, week 4. Okay, bye-bye.